morning. Happy International Festival of Bananas Day. We're going to be covering 1.4, Introduction to Identities. Let me tell you a little bit about bananas before we get going today. When I lived in Malaysia, in my front yard they had a banana tree, so I thought. Well, it comes up that it's not a tree after all, it's actually an herb. And what's interesting about bananas is that you can take that herb and cut it down every year and it grows a new one. And also, you may not know that bananas have seeds about the size of watermelon seeds. And you have to cut off a bulb, and when you cut that bulb off, the seeds don't produce, and that's why you have bananas without seeds, but generally bananas have big seeds in them. So there you go. Let's go forward to 1.4, reciprocal identities and racial identities. Reciprocal identities, we've had this before, but what we're going to see is if we put it in equal form. Now, let's say that we have the sine theta is equal to 1/2, and it's equal to 1 over the cosecant of theta. If you were to solve for the cosecant theta by cross multiplying, you would end up with the cosecant theta is equal to 2 over 1. And you're going to see now that this sine of theta is the reciprocal of the cosecant theta. It's a roundabout way of doing that, but just know that the identity of reciprocal functions that we learned earlier is preserved. They are reciprocal functions. It's just we have an equal sign now, connected now. And so we have reciprocal identities. These are located in the big rock sheet. If I were you, I'd have the big rocks right in front of you and filling these out at the same time. And then when you do your homework, I would keep your big rock sheet in front of you because we're now going to have a lot of identities to draw from when we do our homework. We also want to memorize identities to make life easier going forward. Looking at the racial identities. The racial identities are going to be involving the tangent theta and the cotangent theta. Notice what happens. Tangent theta is equal to sine theta over cosine theta. Well, the cotangent theta is just the reciprocal of that. So really you only have to know the first one, and then with the cotangent, it's just the reciprocal. How do you get this tangent theta equals sine theta over cosine theta? The way that you get that is from the same diagram that we had before. And notice what these are. Those from the diagram are the definitions of the trig functions. So we're starting with the definitions. Then later, you're going to end up simplifying the sine theta and the cosine theta by cross multiplying. When you cross multiply these, notice what happens. You're actually substituting this value in for your y, and you're substituting this value in for your x. And when you substitute those in and cancel your r's, you end up with the racial identity. We've seen this before. I'm not going to spend a lot of time on that, but now that you know where it's coming from, we can just use this racial identity at this point. Don't lose fact of what the important points are and what the supportive material is. The important parts are these big boxes, and then this other part is just the supportive material. In the book, you're going to see that you have sine squared theta equals sine theta squared. The point that this is making here is that this is really equal to the same thing as sine theta times sine theta. Or sine theta squared. Keep in mind the sine theta cannot be separated. It's one unit. Don't unpeel it. let's go to these examples and get to just the general idea here of where we're going with this. We're just going to do the first example, which is if sine theta equals negative 3/5 and cosine theta equals 4/5. The question is, find tangent theta and cotangent theta. Now, very important when you get to these problems. We are going to, at this point, stop using right triangles to help us solve these problems. Up until now, I drew these right triangles in the XY coordinate plane. And now I'm not going to do that. I'm going to use identities that I just established. So do not draw triangles. You have to use identities. You don't want to skip using identities because later on you have to use identities in the problems. These problems you could do it either way, but later on you're going to be forced to use identities and do a lot of substitutions. So we're not going to use the triangle anymore. So how do I solve this? Well, the way I can solve this is know that the tangent theta is equal to the sine theta over the cosine theta. And I'm just going to substitute in values. So these identities are all about substituting. Sine theta is negative 3/5. Cosine theta is 4/5. At this point, you can multiply by the reciprocal of the bottom, or you can multiply top and bottom by 5. So if I multiply top and bottom by 5, it's really 5/1, 5/1. You're going to end up with a negative 3/4. Then you know the cotangent theta is the reciprocal of negative 3/4. So that's just going to be a negative 4/3. Notice the negative sign is preserved when you do reciprocals. These other two examples, 8 and 9, are just substituting in values. So I just want to make a quick comment on this. If you had something like the sine theta is equal to a negative 1/2, what is the sine cubed theta? You're taking 3 sine thetas and multiplying them together, or you're just taking 1/2 cubed. You're cubing both sides, which just becomes a negative 1/8. So those are pretty straightforward. I don't want to spend much time with that concept. At this point, we've learned about reciprocal identities and ratio identities. The third type of identities we're going to learn today is going to be the Pythagorean identities. Pythagorean identities are pretty big in trigonometry, and they're going to come up over and over and over again. And they're all stemmed from the same diagram that we've had. And you're going to see that since this is a right triangle, you can use the Pythagorean theorem for it. So you know x squared plus y squared equals r squared. And that's where we're going to be starting with right over here. X squared plus y squared equals r squared. And all you're doing here is dividing both sides by r squared and then breaking this out as a exponent property. And you're seeing that x over r quantity squared plus y over r quantity squared equals 1. Well, this and this should look familiar. Those are the definitions of the cosine and sine functions. So I can rewrite this as cosine theta squared, and I can write y over r as the sine theta squared. and start with this main identity. Again, don't lose track of the main points here. The main points are in the box. The supportive material is off to the side. At this point, I'm going to get a few more boxes, a few more big pieces of information with the Pythagorean identities. And so the first thing that I'm going to do is divide through by cosine squared theta. If I were to do that on both sides of the equation, what do I get? I'm going to get 1 plus sine squared theta over cosine squared theta equals 1 over cosine squared theta. And to simplify that, it's going to be 1 plus, well, I know what sine theta over cosine theta is. That's just tangent, right? That's the ratio identity that I learned. Tangent theta equals sine theta over cosine theta. So I'm going to substitute tangent theta in here. And I also learned that 1 over the cosine theta is the secant theta. So I'm going to substitute in secant theta for my 1 over cosine theta. And so this right here is another box that I'm going to want to know. I can do the same idea on this part, except for divide by sine squared theta. And therefore, I'm going to have cosine squared theta over sine squared theta plus 1 equals 1 over sine squared theta. Same principle, and therefore I can simplify this. Cosine over sine is the same thing as cotangent. Therefore, this is going to be cotangent squared theta plus 1 equals cosecant squared theta. That's another box. Now, very important, I don't memorize these three. I remember only the first one. This is the main Pythagorean identity, and from this one, I can easily get these other two. Not going to spend a lot of time memorizing these because they're easy to get goofed up. But for shorthand purposes, let's say you're on a test or something, and you see something with tangent squareds and secant squareds in it, and you're like, oh yeah, there was an identity. Well, how did I get it? Well, I would write down in shorthand cosine squared plus sine squared equals 1. And then I would think, okay, if they're tangents, how do I get a tangent? Well, I know it's sine over cosine, so I'm just going to divide both sides by sine squared. And then you're going to see that you're left with, well, this would be the cotangent. So let me back up on that. If you want tangent squared, it's going to be sine over cosine. So you want to divide both sides by cosine squared. 1 plus tangent squared equals secant squared. Shorthand for what I did over here. I would prefer to do this on every time I needed to get these two than to remember those two. So this, to me, is much easier. For you, maybe memorizing it exactly could be easier. The other part of this, which is important to know, is that you can change the form of this main Pythagorean identity by moving things and taking square roots of both sides. For example, if I were to solve this for the cosine theta or cosine squared theta, you can do one manipulation. You could say that the cosine squared theta is equal to 1 minus the sine squared theta. Some of you can easily do that in your head. You can look at this identity and say, oh yeah, that's easy to see. I can just use that from this. I don't really have to write it down. Others of you may have to write it down and then think about that substitution a little bit more thoroughly. You can also solve for the cosine theta, and you're going to end up with that. Plus or minus, because it could be plus or minus depending upon the quadrant. And, oh yeah, by the way, one thing that you may want to remember what we covered yesterday is SATC. I didn't really write this down before, but we're going to remember, you could say all students take calculus, but that's somewhat boring. Instead, I will always refer to this as the Santa Claus concept. Why? Because you have Santa Claus on the bottom, the way you read it. The benefit is, it's the way you read, Santa Claus. Plus it's fun to say. The drawback is, it's not in the order of the quadrants. All students take calculus is in the order of the quadrants. That helps, but it's boring and not true. And it may hurt your feelings if you don't go to calculus. So, we're going to say Santa Claus, and that's going to be the principle on where the trig functions are positive or negative in the particular quadrant. Let's go to this example. This is sine theta equals 3/5, quadrant 2. Solve for the cosine theta, solve for the tangent theta. Do not draw these in the quadrants. We're going to use the trig functions. That's why you should have your big rock sheet out in front of you. And now you could have a lot of this filled out. Identities, definitions, special right triangles, Santa Claus as well. So we're going to go through this and figure this out without drawing triangles. Sine theta equals 3/5 in the second quadrant. I want to find the cosine theta. Well, I know that the cosine squared theta is equal to 1 minus the sine squared theta. That's one subtraction from the main Pythagorean identity. And then I can take the square root of both sides. And now I want to substitute this value right in for the sine theta. This requires some fractional work. Remember, 1 is the same thing as 25 over 25. Subtract them off. And you're going to ultimately see that the cosine theta is going to be 4 over 5. The plus or minus refers to Santa Claus, so I'm in the second quadrant, which means in the second quadrant, the sine is positive, the cosine is negative, therefore I put the negative out front. A lot of mistakes will be made right there. Don't forget about Santa Claus. Tangent. Tangent is equal to the sine over the cosine. I'm going to go ahead and plug these values in. 3/5 over negative 4/5. You could multiply by the reciprocal, or you could multiply by 5 over 5 on both sides, top and bottom, which means that this ends up being equal to negative 3/4. And that's the same thing as 5 over 1, if that makes more sense. All right, so what did I do here? I used the Pythagorean identity to figure out what the cosine theta is from the sine theta. And then I used the ratio identity to evaluate what the tangent theta is and plugged in for the sine theta for the cosine theta. Let's do another problem. Again, we're not drawing triangles. I want to go ahead and figure out what this is by only using identities. I'm going to put in cosine theta is equal to 1/2. Notice how I listed these. Sine theta, cosine theta, tangent theta in that order. The reason why I did it in that order is to, again, help me in the long run. Sine over cosine is tangent. All I have to do is divide these two numbers to get my tangent. So I'm setting it up in a way to make life easier. Secant theta is the reciprocal, or 2. Then I want to go ahead and solve for the sine theta. Now, I did the first one by just writing down, solving for the cosine theta. A different way of doing this is where you actually just plug it into the main identity and then solve. So you may prefer that method. But the main identity is cosine squared theta plus sine squared theta equals 1. Plug in what you know. And then evaluate what the sine theta is. So this will be 1/4. Subtracting 1/4 from both sides gives you 3/4, right? 4/4 minus 1/4, 3/4. Take the square root of both sides, and it's a plus or minus. So the sine theta is equal to, again, in the fourth quadrant, Santa Claus says in the fourth quadrant, cosine is positive, the others are negative, so that becomes a negative radical 3 all over 2. Being careful where I draw this line to show that the 2 is not under the radical. Therefore, sine theta equals negative radical 3 over 2. Cosecant negative 2 over radical 3. Honestly, at this point, it doesn't matter to me if you simplify that radical. You just need to be able to recognize that that's the correct answer, and this is the correct answer by simplifying that square root in the denominator, or rationalizing the denominator. The tangent, you're just dividing them down. This becomes negative square root of 3, and this becomes I'll just write it down to make it a little bit easier. And then you could actually multiply by, well, you could multiply the top. You want to get rid of that radical 3, and this by radical 3. This is going to be a little bit messy. I'm doing it the hard way, but negative 2 over 2 square root of 3. And then the 2's would cancel, and so you're left with radical 3. Negative. Now, one thing you could have done is divide it down like I did. A simpler way to do this is to look at the tangent theta and do the reciprocal of the tangent theta, and that's what you would have gotten if you did that. So you could divide down, or you could use the reciprocal of tangent theta. That's all I have, so you can start your homework now and enjoy International Festival of Banana Day.